I'm William Mullane, and I work in the Science Operations Center in the European Space Agency in Madrid, Spain. I'm the GAIA Mission Manager, and so I'll tell you a little bit about GAIA and its current status, and a little bit about data processing, which is one of the areas we work on in the space agency here. So here's a little outline. I'll go through all these points in an organized manner. So a little bit of the GAIA science background, the satellite and the mission, a little bit on the GAIA data processing, the commissioning, which we just finished in July, and what the status is after that, and then just a slide with some conclusions and questions. And I think these slides will be available to everyone afterwards, and at the back of it, there's a lot of reference documents and list of acronyms, because I'll use a lot of these three-letter acronyms, which all space agencies are very, very fond of, and nobody understands, including a lot of the people who work in space agencies. So GAIA Science, I always like to start with this Tintoretto painting, because it's people ask, why do you build satellites, or why do you do science? And if you look at this painting from 1500, this is only a few centuries ago, and people were still of the opinion that the Milky Way was breast milk sprayed from the breast of Juno when Hercules was lowered down by Jupiter to make him invincible. So the whole point of something like GAIA, when people ask me, why do you go measure stars and why do you want to know about the universe? Well, it seems we should advance our knowledge a little bit. We want to make a better model of our galaxy than that it's milk, because it looks like milk. So here we are in a more modern picture of a galaxy that might look like ours. And we're way out here in one of these spiral arms with our sun, and in between we have a lot of dust between us and the center of our galaxy. And we actually don't know very much still about where our galaxy came from and how it's formed and how it's interacted with other galaxies. So our aim with GAIA is to unravel the formation, composition, and evolution of our own galaxy. And by doing that, to learn a little bit more about galaxies in general and formation of galaxies in the universe. So, again, just to give you some words that come up, like parallax, parsec, what these mean, and give you some idea of the distances we're talking about. Again, this is another Milky Way, a little bit like ours, if you want, where we have a bulge in the middle. There's some sizes on these, 3 kiloparsecs. So a parsec is a parallax of 1 arcsecond. Now, a parallax is when you look at a star from both sides of the sun during the year. When you look from one side and the other, the background stars seem to move a certain amount. And it's not really, it's just a parallax effect. If you move your head from left to right looking at 2 poles, you see the same sort of effect. And it's a measure of 1 arcsecond movement for a star like that. And it's equivalent to 3.26 light years. That's the distance that light will travel in 3.26 years. So these are huge distances that we're talking about here, out to 30 kiloparsecs. Our galaxy is very, very large, considering how small we are. So GAIA, what it wants to do is to build up a map of stellar motions. And when we have this map of positions and velocities, we can then predict and go backwards and forwards. So if we look at the map of all of the stars as we gather them, and then we look at the movements of those stars, they'll have a similar angular momentum if they came from other galaxies. So this little graphic here is trying to show you how our galaxy has consumed other galaxies during its lifetime. Or maybe they consumed each other, however you want to look at it. And the stars wash in and out of the galaxy, and you get this kind of stream, tidal stream of matter as a result. Now, we should also be careful that when galaxies collide, it's not like a car crash. Our galaxy is full of space. There's nothing in it. There's millions of stars, but it's so large, there's lots of space. So typically, when your galaxies collide, you're not seeing stars colliding with each other, they're just passing by. So what's happening is the orbits of these stars change. And so you get this kind of swirling around the place. You don't get a big crash of, lots of planets hitting each other and stars hitting each other. It's quite funny. So this is a graphic if you want a simulation from some of these red lines. But here's a real picture of a galaxy, and you can just see in the dust streams the same sort of effect that the models predict. So our telescopes are getting better. We're beginning to already see these types of the reality of how our galaxies consume other galaxies. Then what about GAIA? What do you need to do this? So there's a paper from 2001 expressing what you would want to do. So you need a representative sample of stars down to the same magnitude. So you need to have a lot of these distances and motions. If you really want to combine the stars, you can't just look at the motions. You should really look also at their methodicity. Are they the same group of stars? Do they come from a similar galaxy? The current predicted accuracies for GAIA, so some of your astronomers, I think, will understand the terminology here. But what you're seeing is that we will see very, very accurate positions of less than of order of a few microarc seconds for most stars. And as we get to fainter stars, a few hundred microarc seconds. Now, Hipparchus is in a milliarc second, so we're much, much better at the same level than Hipparchus did in the previous space astrometry mission. As well as the astrometry, the precise measurement of positions, we will add in some photometry, and for that, we need that for the astrophysical diagnostics and for chromaticity correction. We need to know the colors of the stars, and spectroscopy, because when we measure positions on the sky, we can't tell if the star is moving towards us or not. Plus, we get chemistry from that. Just to explain perhaps a little bit of microarc second and what that means for people, and also the evolution. Here you have on the left side of this picture Hipparchus, who is the Greek astronomer from 129 BC, and he was able to measure basically 1 degree, and that's about the size of a person 100 meters away from him. So that was as good as he could do. He was probably doing that with his finger or something like that. He's shown here with a telescope. Tycho Brahe improved optics and bought us some mirrors and things. He was able to get down to, a fraction of a degree, a few hundredths of a degree. And then we've done some modern astrometry. So with bigger telescopes and better optics, we're able to get down to a few arc seconds. And that's really quite good. That's the size of a man 4,000 kilometers away. Now, Hipparchus went to space to show that you really need to go to space to make very accurate measurements of star position. And we went down to a milliarc second. And that's the size of a man on the moon, if you want, who were standing on Earth going to look at him. So GAIA will go the whole next order of magnitude below that, from microarc to a microarc second, or a milliarc second. And so if you want to put that in context, it's like that guy on the moon that you could see with Hipparchus, you could see the euro coin in his hand. So that's what a microarc second means. I think the other good thing someone said to me once, a microarc second, if you look in the audience at someone about a meter away from you, in the period of time that I was saying this sentence, their hair will have grown 1 microarc second. But just to give you an idea how small these angles are. Why do you need a satellite? Well, you have to go to space because on the ground with our telescopes, we have a lot of atmosphere and there's a lot of other problems. Temperature, telescopes are not stable enough to make these very, very accurate measurements at such very, very small distances. Even something like the waves beating on the beach a few kilometers away can interfere with a measurement of one arc second. And at 1 microarc second, anything, a car passing a few kilometers away will be enough to disturb your measurement. So our closest neighbor, as I put on here, that's also out of interest, has a parallax of 1 arc second, and that's about as good as you can measure on the ground. So the fact that we've discovered parallaxes and of stars at all to give distances and motions is actually quite interesting, or quite good astronomy done long ago, that they were able to get to this good a measurement. It's about the limit of what we can do. Adaptive optics and things get us a bit better, but we don't really get there. So a little bit more about GAIA, the satellite itself. Just to tell people in case they don't know, GAIA is a European Space Agency cornerstone mission, cornerstone 6. So the Space Agency had larger and smaller missions. This is one of the larger missions. It's an ESA-provided hardware and launch, so the entire satellite construction and launch is paid by the Space Agency. Often instruments are provided by institutes, not the case for GAIA. In GAIA's case, it's such a combined instrument, we built the entire thing. It was launched in December of last year on the 19th from Peru in French Guyana. It's supposed to go scanning the sky for 5 years. And we have a potential extension of 1 year. So typically the space agency says you have a mission of X years, plus you should size for an extension of 1 year or X years. And then you may get more than that, depending on financial situations at the time when you get there. So we have a good 5 years and probably 6. We have fuel on board after commissioning for about 9 to 10 years of operations, and that's our limiting factor. There's no cooling on Gaia, it's all passive, so we have no coal gas and things like this, which we will run out of. Well, sorry, we will run out of coal gas if that's what we use for propulsion, and that's our limiting factor more than anything else. And then we do microarc-second-metry, so as I said, about 1 billion sources of 20th magnitude. Again, it's one of the interesting things of astronomy. We don't know exactly how many stars we have at that magnitude. There's no really good census. We should have one when we finish Gaia. Radio velocities and photometry I mentioned before. And the final catalogue is due in 2022, but we won't let you wait that long to get some information from us. You'll get something about 2016. So in a couple of years, we'll have the first catalogue. It won't be the final accuracy, and it won't have all the information in it, but it'll be a good start, and it will be a big advancement for astronomy. The picture here on the bottom is the internal structure of the satellite. It's a silicon carbide torus. And I think I'll say a few points just about the hardware. There's a lot of novel things in a lot of science satellites for the space agency. In fact, they're nearly all completely novel. It drives a lot of the European industry to come up with interesting ways of doing things. And we pay for a lot of research that then gets fed back. This is true for all space agencies. I mean, this is one of the reasons that we can sell space exploration to governments, because they get some feedback on technology. So the torus and mirrors, that structure I showed you in all the mirrors, and most of the satellite is made of silicon carbide, which when we were building it was a fairly unique material. Now it's being used by practically everyone for satellites and even radio antennas on ground. The clock distribution unit, it's the first rubidium atomic clock flown to L2. So this is more accurate than what you have in GPS satellites. We need very, very accurate timing. Passive cooling with radiators, this is a very common technique, but still we're getting down to good temperatures by just using passive cooling, which means you don't have to throw coolant. We have 7 video processing units. These are like a PC if you want. It's a very old PC by your standards. It won't be as powerful as the machine sitting on your desk most of you have these days. But you know, everything has to be space qualified, and your technology is a few years old by the time you launch it. So these are very, very advanced boards for space, and we have 7 of them instead of the usual 1 or 2 that you will have on most satellites. All the onboard software is also quite interesting in that if you consider that on ground and even from satellites we have detectors where normally we make observations, we do an awful lot of data processing to figure out where the stars are in the picture, and then we figure out the positions of the stars like from the picture afterwards. All of this is done on board on Gaia with those processing units. So Gaia is looking at the stars and pulling them down individually. So this is quite a big step forward. It's quite a complicated piece of software to fly the satellite. The phased array antenna is something quite unique as well. We can't have moving parts on Gaia. It will disturb how the observations are made. So nothing moves on board Gaia, including the antenna. So the phased array antenna is an array of antennas effectively which allow you electronically to steer the beam that's coming from the satellite towards the ground station. This is a quite interesting technology. And then cold gas micropropulsion. We looked into electronic propulsion systems and we failed to get a safe enough one to use for launch, so we went back to micropropulsion of cold gas. But this is a system where you can get 1 micronewton of thrust from this cold gas system. Very, very accurate propulsion system. Again, we need this for our measurements. And then the attitude and control system, also quite unique on Gaia, because it's tied to the star mappers and the instrument itself. And typically for science satellites, these things are not at all tied together. So it's a survey. As I said, it's not an observatory. So again, if you think of ground telescopes and things like Herschel, you make a plan or you make a request to observe particular stars, and then Herschel makes the observation, or the satellite makes the observation, or the ground telescope makes the observation. In the case of Gaia, we're just going to scan and see everything. So Gaia is just spinning around in the sky for 5 years. following a specific scanning law. And if you plotted out the number of observations, the map that's down here at the bottom, the green is about 100 observations of that patch of the sky. So any star in that patch of the sky will be seen about 100 times. And the average over the whole sky is about 80. And you'll see there are no black bits. We see every bit of the sky at least 40, 50 times. And some of them very, very, very frequently, several hundreds of times in the nexus points of crossover. Just a small aside, I was asked for interesting material for background. This is a very interesting book. Michael Perryman was the project scientist for Hipparcos, and he was also the original project scientist for GAIA, but he left the space agency some years ago. But he did write this very interesting book, which I found fantastic to read, not just because my name is mentioned in there, but because it was very interesting book to read, very easy to read. And so it's something I think which you might enjoy if you would like to know a little bit more about how he built these satellites and how they go through launch and the tension that we experience as we watch these things going on. It's very, very good. And he's called it the making of history's greatest star map, because that's what Hipparcos catalog was a few years ago, but we're hoping in a decade to replace that with the GAIA catalog, which will be history's greatest star map after that. Of course, we'll get replaced by somebody else in another 20 years. GAIA data processing. So inside that torus, the detector, the camera, if you want, this is a picture of our camera. Depending on the projector that you're looking on, you might have seen this about light size. It's over a meter in diameter across this detector. 106 ccds. It's almost a gigapixel. So your camera still only have a few megapixels, and we're flying a gigapixel into space, just to give you an indication. So any one of these little CCDs here is a little bit bigger than what you would have in say an SLR camera with a large CCD. What actually happens is the telescopes reflect the light through the two different telescopes reflect light onto this focal plane. So this animation is just showing you the reflected starlight as it comes onto the focal plane. It drifts across the focal plane and then spread out by a prism for the photometers and the spectrometers. And as I said, the video processing units are detecting the stars in the first two columns here, the star mappers 1 and 2, to decide which telescope it came from. Then it's tracking it across the focal plane. It's not taking a gigapixel picture, it's merely taking a cutout of each of these stars. So our data processing is rather complicated. If we want to make a map with microarc-second accuracy, we have to get the centroid on the CCD image about 1% of one of the pixels in those CCDs. We're going to have 10 to the 12 images because there's about a billion stars. We're going to see them hundreds of times. And each CCD image coming out of that. So if you add it all together, it comes to about 10 to 12 little images, about 100 terabytes of data. That's highly compressed. When we decompress it and we do some processing on it, we will have to deal with about a petabyte of data over the years. When we were talking about this 10 years ago, that may seem very, very big, but we did realize that technology is catching up. And these days, it doesn't seem so difficult to have 100 terabytes or a petabyte. And indeed, our systems are coping very well with the first 5 or 6 terabytes that we've already downloaded. But if you think about that as a millisecond per image, it's 30 years. So we do a lot of parallel processing, a lot of distributed processing on lots of computers simultaneously. And the total processing estimate to produce the final catalog about 10 to 20 slots. Again, we have supercomputers that could produce something like that in a few weeks or a few months. But getting the data through it and getting it all done is a bit trickier. Plus, we have to actually acquire all the data first. If you again want to make microarc-second observations, you need to have the attitude of GAIA. So spacecraft attitude is the three-dimensional orientation of the spacecraft, and you need to know the orientation of about 2 microseconds. Therefore, you also need to know the path of the light through the instrument at about a nanometer level. Not too bad, but pretty tricky. And you have to have an extremely stable system, so I said we have no moving parts. And if you're down at this level, light doesn't travel in straight lines anymore. We have to take account that if we're looking at a star and Jupiter happens to be somewhere within a few degrees, even 80, 90 degrees of where we're looking, that light will not be traveling to us straight. So the star is not where we think it is, or it's not where we observe it to be. It's a little bit in a different direction. So these type of things are all built in. Now, the only way that we can calibrate GAIA and get the attitude correct and get our geometry correct is by using comparison observations. So sometimes it's considered to be a self-calibrating instrument. By looking at its own observations, we will detect, because we see the same star 80 times in different orientations, we can detect flaws in the instrument by averaging over all of these things. This is called the astrometric global iterative solution. I'll come back to that very, very briefly. So testing and verification of all of this was very, very difficult. And in fact, even though we've launched and we now have several parts of the processing system in operation and running, there are still other parts that are in operational rehearsal because they won't come online for another year. The general relativity is, you don't always think of that with astronomy observations, but because of light bending and everything else, we do have to take account of this. So what we're actually observing with GAIA are distinct points in time events where we've seen a star, and so we need a very accurate time for that. And then we have to have some very good software that also takes account of, as I said, light bending from planets. And when we put all of this together, we can go back and we can look at all of our data together. We can extract probably some, general relativistic parameters, post-Newtonian parameterization, such as gamma, or something like this. There's 4 or 5 parameters which we can look for in our data set. We can probably give some new values to these things. They're like constants, but it's always nice to check them. It's also a nice check for our software. If we get a wildly wrong value for these Newtonian parameters, either we get the Nobel Prize because we've proved general relativity is wrong, or more likely we made a mistake somewhere. So it's a good check for us to run as well. So the spectroscopy and photospectroscopy, these are both quite difficult. We want magnitudes of millimagnitudes. And as you saw on the cartoon I showed earlier, the little animation, what you have is a dispersed spectra or dispersed light. It overlaps. If the stars are close together, you're going to get these bleeding into each other. So it's not the way that people do spectroscopy normally by plugging fibers into something and cutting out the rest of the light by putting a halo around it. So this is also quite challenging. You have to extract the signal from this, disentangle it, you have to calibrate it, you have to put dot scales together. We will then have GAIA's own scale, and we'll have to tie that back to what people expect. So we'll make some specific ground observations of some stars to give us some 0 points for these things, so that we can relate them to what astronomers expect to see. Spectra for 100 million stars, more or less 16.7 magnitude, about 40 times each for those. Why is there less? Well, if you look, the spectra of CCDs are just a few rows, not all rows, so we don't see all stars with the spectrometer every time we cross the sky. We also couldn't afford to downlink the spectra, they're too big, so calibration is difficult. So the downlink, closer to home, Cebreros is our 35-meter antenna dedicated, well not dedicated to GAIA, but the one most, let's say. It's about 25 kilometers from where I'm sitting right now, talking to you, in Cebreros, just a little bit from the station here out in the countryside, in a nice, remote, quiet area. We get about 3 to 8 megabits per second downlink. Again, L2 is a long way away, 1.5 million kilometers, and we're just transmitting this X-band signal back. So it's a very good data rate for space, but, in your terms, down on the ground, it seems kind of quite weak. And if you do the math the other way on this, you see you get about 30 gigabytes a day, and you end up with about 100 terabytes in 5 years. Doesn't mean if we go on for 6 years or longer, we get more data, of course. We will also use Norcia in Australia, so a little bit further over on the other side. Sometimes we need, so the point of having 2 antennas on different sides of the Earth, of course, is that GAIA has always been the same place at L2. As the Earth rotates, we can't see it with Cebreros, so occasionally we'd like to get more downlink, so we bring online Norcia. About 20 days a year we use that to get some when we have very, very heavy data days. So you've got hours of which antenna we use when. This is all proved up by the Mission Operations Center in Germany, and we predict what that's going to be with a model of the sky. It also provides the station delays, which we use. So the data flow is, as I said, 30 to 50 gigabytes a day. 30 from the satellite, but when we do a bit of processing, what we actually send for data processing centers is about 50 gigabytes, or a little bit more, in fact. We use an Aspera fast for this. It gives us, we have it actually throttled at 300 megabits per second, so we don't swamp the gigabit line going out of here and annoy all the other people in the center. This is working very well. We can transfer our data on a daily basis, no problem. When we pull all the data together and we have the full catalog in a couple of years, the first version of it, then it starts to be a question when we have to start sending a few terabytes instead of a few megabytes. Even so, we've done transfers of 1 terabyte in under a day. This is not really a problem. When we start having hundreds of terabytes, maybe it starts to become a problem. So we still have to think about whether we, in the end, may need to ship. So I'm still hopeful that the networks will improve and the technology will be there in a couple of years for us to use it. There's a lot of upgrades of lines around Europe, so hopefully they'll just be able to send this stuff as well. Plus, we don't have to send it in 1 day or 2 days. It can be sent over a few weeks in batches. Just put it all in the cloud. Doesn't really solve the problem, the up and down problem. Still have to put it there somehow. Anyway, as I said, it's not a problem for us just yet, but it is one of our, one of those niggling things in the back of our minds we dealt with. This is just a plot of the data volumes that we've taken in commissioning, so up until the 1st of September, so a few days ago. And what you see here is what we've downlinked from the satellite, I just checked today, 5.7 terabytes of science data already. As we process that, our operational database, it grows to a much larger size. So what you're seeing up here is nearly 50 terabytes database. Because when you do the processing and you make reports and you make analysis, and then there's results and averages, and it starts to grow quite quickly. And we won't let this grow to several hundreds of terabytes or 1 petabyte database. Typically, for operations purposes, we see data maybe up to 1 or 2 weeks old. So we need to keep data for a month to make a proper daily solution, do proper processing, spacecraft attitude. But after that, we can probably ship it off to the long-term store. So we hope to keep the nominal database around 10 to 20 terabytes. We're just doing a cleanup for that at the moment, post-commissioning. Data Processing Analysis Consortium. So GAIA hardware was provided by the Space Agency. The launch was provided by the Space Agency. And the data processing is mainly done by the European Community of Scientists. This involves rather a lot of European institutes and observatories of about 400 people and 20 institutes. The science community is doing all of that processing. It's led by an executive, and there's a project office doing management and planning. A steering committee which looks after financial arrangements. So just to give you an idea of numbers, here's a slide with DPAC members. You see there are people spread out all around Europe. Quite big numbers in Spain, UK, and Italy, and France. And less elsewhere, but significant contributions from different places. And there are data processing centers, which I mentioned. So we ship data from Spain to France and Italy and the UK and Barcelona from Madrid. Coordination units are how this is all organized, if you want. Each unit is a specialized area. So one is system architecture, simulations, which are less important now, but were very important during processing, during the development. Core processing is the astrometric solution and the daily solution for astrometry, etc. Object processing is for detecting those binary stars and dealing with all of the funny things that don't look quite the way we expect. Well, we expect, but not for the standard processing. Photometry for color, spectroscopy, variability processing. So a lot of, if you look with enough precision, all stars are variable to some extent. They wax and wane a little bit. So it's an important issue for us to work with light curves and what's the variable period of stars. And then astrophysical parameters are all of those things like methodicities, etc. ESA has a significant contribution in 3 or 4 of these areas, including catalog access being committed. Data processing centers, as I said, there are 6 of them. I won't go into them. They basically back up those different coordination units running the software that's developed by those different people to produce the reduced data from those different areas. So how does that all look in terms of processing? So we have GAIA up here in the top left of this diagram. It's spinning around, it's making observations of stars at different times. And this is downlinked to us in Spain eventually. And then we do what we call initial data treatment. So taking those CCD transits and turning them into what an astronomer would consider an observation for time and a position on the sky. That's a relatively easy transform. There's a few wrinkles in it, but it's not too difficult. It's mainly calibration of the instrument and taking into account some effects. Then we come to the next level of processing. So when we want to make the astrometric catalog, we look at all of the stars together. So we do the astrometric treatment. We fix the geometric calibration, we adjust the spacecraft attitude, and we fix the source position. That's also done here in Spain. The software is produced by the CU3 with some contribution from the team here in the The photometric treatment is done in the UK, so that we calibrate flux scale, giving us back the magnitudes and colors, and then the spectra treatment to provide the spectra calibration disentangled. Once all of those steps are done, the next level of processing happens. So then the solar system objects can be extracted from that relatively easily, and we can start orbits for asteroids, etc. Variability processing, but you need to have the photometry information for that first. Astrophysical parameters like metallicities, those you need the colors and the spectra, and then the non-single and so you need astrometry over many years to figure out which stars are binary from the astrometry correctly. You need many observations. And then once you've done that, they all feed back into each other. So you iterate through this whole process many times until you get a catalog. So that's why we can have several catalogs. We can produce one at a certain point of processing, and then we'll produce a much better one a few years later with more data included. Just a question of, well, what does data reduction mean? In the end, what you're having is a catalog, but you're taking hundreds of terabytes of data and you're making hundreds of observations of stars. And in the end, you want a few numbers back from that. This is a minimization problem if you want. It's taking what you observed and trying to model it to see if you can construct a model which matches your observations. So I'm not going to go through this slide, but I put it there for people if they're interested in it. I've explained what it wants. You can go back to the Hipparchus catalog and see that in a bit more detail. And I put a reference here to a paper, which this is a very simplified model. The actuality is a bit more complex than this. And that's described in a paper from Lindegren 2012. And it's, well, if you have a mathematical bent, it's a very interesting paper. If you don't, probably not. Putting this in a sort of more accessible form, another cartoon here, it's effectively, how do I find the best catalog parameters? So on the left here, I have the right ascension destination, the parallax, and then I have the proper motion in three directions. And effectively what I'm saying is, what are the best set of numbers for my hundreds of observations that can predict where I should see that star on Gaia CCD? And that's effectively what the astrometric solution is trying to do. So again, there's a paper from me from 2011 about the implementation of the equations which are in the 2012 paper. I know they're the wrong way around, but that's just a publication thing. So you can go and look in a bit more detail of those things if you wish as well. But that's a kind of high level, if you want, how do you fit simple observations to a simple catalog. So I'd like to wrap up soon, but I would like to show you some commissioning things. So we listed off 1912, 6:12 a.m. Zulu time, so that's GMT time. And that was at dawn, so it was just the sky going blue. A photo here from of the satellite as the rocket as it lifted off of the Soyuz. Then that was all perfect, and we were put in perfect orbit in a fantastic Russian launch from French Guiana. That's a new thing for the Space Agency. We partner with the Russians now launching from the European Spaceport in French Guiana. On day two, we did the crucial maneuver of firing the starter to send us off towards L2, and that was again perfectly executed by our friends in Germany in Flight Dynamics. And then on the way, we started heating up the satellite to decontaminate and get rid of any water. Contaminants inside, and at that point we were going to L2. And then after a few days, on January 3rd, we actually flipped the switch and started turning on some of the instruments. And then from January until July, middle of July, we were in what's called commissioning, where you do a checkout of all of the different instruments. First thing noticed, a day after launch, we had many amateur astronomers taking pictures of Gaia, and we discovered that it was much fainter than was expected. So the sun shield is better than we expected. We thought Gaia would be 19th magnitude at L2, and we would be able to observe it with sort of 2-meter telescopes. That's not the case. It's 20.5 magnitude, so we need bigger telescopes. And we can also do these differential one-way requests from Mach with the radio antennas or VLBI. So it's not a disaster, but it was interesting. So I said we switched on the instrument on the 3rd of January, and if you saw this picture, you might think, oh, that's terrible. We were so happy to see this picture because this is the first indication that Gaia works. The CCD turned on, but Gaia is not spinning. And Gaia is meant to be spinning, so what you're just seeing is the stars zipping across because the satellite's not moving. So these white lines are actually stars crossing the focal plane. So we were very happy. Then we started spinning up Gaia a few days later, so this is more like what you would expect. Millions of stars. And here you can see quite clearly the next thing that you have to do in commissioning. There's a double peak in this star which shouldn't be there, and that's because Gaia is not properly focused. So we started to do focusing, and we were very, very happy with this as well on January 8th, so a few days later we're spinning, we see things working very well. And then, as I said, focus is a tricky thing for Gaia, because you're spinning, the focus and the readout rate and the spin rate are all intertwined, so it's not as simple as turning a little dial like you do on your camera or your home telescope to get the focus. It's a very iterative process, and it took us a few weeks to get it working properly. Here's a couple of pictures of the Cat-Eye Nebula, which you can see on the right-hand side. A defocused picture could be the spin rate, could be the focus, and on the left you see it starting sharpen up. I should point out, again, you make these type of images on the ground, typically with maybe several minutes of observation and overlays. These are a few seconds with Gaia, just to give you an indication. It's just a transit on the CCD, so it's typically 4 to 5 seconds, 6 seconds. Here's another image which I hope it shows another characteristic of Gaia. We should also bear in mind that Gaia is not an imaging instrument. We do not make images like this. We detect stars and we download positions of stars in very small cutouts. But we have a mode where we can make images. And then you see interesting things like here, a big black gap between the two images, because this is imaged on 2 different CCDs. And we have gaps between our CCDs. Not a problem for astrometry, but it's a typical telescope problem if you're making these type of pictures. You have a fill-in to do afterwards. So you need to make another observation. This is M94, and just showing you how there's a large gap in between. The other problem that we have with Gaia CCDs, and you may have seen some of the PR images, and you may have detected in something like this, for example, that it's a bit stretched out, and that's because the Gaia CCDs are rectangular, they're not square. Most of the image processing software is using square pixels. Some of the PR images we fixed that up properly, but for some of these we don't because we understand all of them. So that's pretty much it. Just one roundup slide. Gaia hardware is commissioned. The mission's on. We're taking data rapidly, and we're starting to work on it. Well, we've been working on it for several months. And we're working on it even more to get a catalog out. A couple of issues which you may have seen out in the press or on the blogs. We do have a little bit more stray light than expected. The accuracy that showed in the earlier slide take account of that already. They're the accuracies including the stray light SSS during commissioning. So it's still quite good. We still get pretty much what we wanted from the astrometry. We do lose a little bit on the spectra on the faint end, so we lose about almost 1 magnitude in spectral. And we probably compensate a little bit for that by only taking high resolution and no low resolution spectra. There is a basic angle variation, which is something very bad for us to some extent, because we wanted a very, very fixed basic angle, a very stable telescope, and what we've got is a slight fluctuation. But we know that because we have an instrument that's upward to measure it, and by measuring it, we should be able to take it out in the processing. it just makes our life a little bit more complicated, so we'll see how we get on with that. We're still seeing some contamination, so the outgassing done originally didn't remove all the contamination. We have decontaminated since, and we've gotten rid of more of the contamination, but it's come back. It's come back more slowly, so we have some hope that we can remove this in the next year. It degrades to a little bit below in faint end of the stars somewhat, but it's something we can deal with. It's a kind of normal thing for satellites, just a bit worse than we expected on GAIA. So DTAC forces lots of data so far, which is very, very good, and if we continue doing so, and producing the catalog. And, I always think people see space missions and it's a huge number of people and very innovative hardware, very innovative people, lots of software, and it all has to work together over many, many years to produce that catalog for everyone in 2016. And it's a big job. So that's the end. A few links here, and again, if the slides are put up somewhere for you, you can click on those links. You don't have to try and write them down. You can also just search for GAIA ESA homepage, and you'll get a first link on Google, I think, or second, if not the first. And then there's interesting tool there for the amateur astronomers among you, although you need a pretty big telescope, but you can ask GAIA, when will you see a particular object, and we can give you a fairly good idea of when GAIA is going to be looking at a certain patch of the sky. So you can look at it at the same time. The radio astronomers are most interested in that, though. And you can always send questions to the help desk. And I'll stop there, and that's the end.